good evening from the ABS in Canberra. And on behalf of the Statistical Society of Australia, I would like to acknowledge the traditional custodians of country, in particular the Ngunnawal and Ngambri people of the Canberra region and their connections to land, sea and community. And we pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples present here or online today. Welcome everyone. My name is Luca Maestrini. I'm the current president of the ACT branch of the Statistical Society of Australia. And we are here today for a talk which has been advertised as part of the National Speakers Program of the SSA. So we have many people joining us online from across the country. It's my pleasure to introduce the speaker of tonight, Professor James Brown from University of Technology, Sydney. James joined UTS 12 years ago from the UK, from University of Southampton. And since 2021, he's been head of the mathematical science discipline at UTS. In his research, he's been collaborating with National Statistical Institutes for nearly 30 years, particularly on census coverage, management and adjustment. We will keep all the questions for the end of the talk. Feel free to post your questions online if you have any questions for James. Thank you, James, and we are ready to hear you. Yeah.
Thank you very much, Luca, and thank you very much for the very generous invite to come and talk to you this evening. Just at the very start, I should recognise that the work I'm going to talk about tonight, particularly the two examples that I'm going to work through, come from work by two of my PhD students, Imam and Ika, and my co-supervisors at UTS, Joanna Wang and Stephen Woodcock. So this is work that very much the examples that I'm going to talk about tonight come from the work. And in fact, I'm going to talk about a tiny bit of the work that these guys are actually working on, but to demonstrate something. And as we're coming here, I thought, we're going to talk about official statistics of combining data. And I thought, this popped up in my LinkedIn feed just earlier this week. But I think a very timely reminder of obviously how important it is when we can combine data in new ways to actually improve the statistics that we produce. And I think obviously that's a fairly exciting. If you're a mortgage payer, you probably wish ABS had got it out for July, because then they might have put the interest rates down in July instead of waiting for the quarterly data to come out. So very exciting. So what I'm going to do tonight is I want to go through these two examples of ideas of combining data. And I think probably many of you will be familiar with both of these things. So I'm just going to touch on a couple of different ideas that we've been playing around with in these spaces. So I'm going to talk about this idea about small error estimation. So for people perhaps who aren't so familiar with it, I'll give you a very quick introduction about the basic idea of small error estimation and the sort of standard approaches and the particular approach that we're looking at. And then the thing we're going to do is look at this idea of bringing in auxiliary variables into your model for small error estimation that have measurement error. And this is not, this is not an idea that we've come up with. It's been around in the literature for a while. We've been trying to play around with it, do some simulation work and understand how it actually functions. And then I'm going to switch to the second one, which is this population size estimation, this idea when you have two sources trying to estimate the size of population. And what I want to do there is going to dig in, do a little bit of a reminder about what it's about, set up this particular idea with two sources, and then explore an idea that we've been playing around with using latent class models with only two sources, which is a little bit different to some of the other latent class work that's been done before, particularly that Bernie did in his PhD, where we had multiple sources and brought in a latent class structure. So straight into a small error estimation situation. So this is the problem for those of you who are not so familiar with this. The idea is I've got this set of small areas in my population. There often are literally geographic areas. They can be subdomains as well. And I've got this survey-based estimator, typically some kind of standard direct estimator, model assisted or design-based estimator. And that estimator is driven primarily by the units in the sample. from that area. And the problem is in a small area. So what do we mean by small? Small area in this case just means an area where the sample size is typically too small for you to be able to publish those estimates because the standard errors, the sampling error is too large. So it's a bit like a talk where someone said, what's big? How big is big data? Well, your data is big when it doesn't fit conveniently on your computer, really. And in this case, small area, yeah, there can be quite large geographic areas in a country or quite large domains, but the sample can't directly support them. And Ika's, this is Ika's PhD work, and her interest in this is coming from Indonesia and thinking about the UN's Sustainable Development Goals there for Indonesia, and thinking about the fact that there are a large bank of these indicators that a country needs to estimate on its progress in the Sustainable Development Goals. And they need to be not, it's no good just estimating them, big national pictures or big state level pictures. You've got to estimate them down at low levels. And so we're thinking about this in the context of what in Indonesia would be called their sub-district level. And that's kind of the level below where most of their big surveys can operate. So most of their big surveys can give you what they would call a district level estimate, which is already a fairly low down estimate, but they want to get, for the Sustainable Development Goals, they want to get down to the sub-district level. So I'm not going to show you any, Ika's goal in the end of her PhD is actually for us to produce some genuine estimates for the organisation, but I'm not going to show you any of that data tonight. I'm just going to show you a little bit of our exploration that we've been looking into. So how do we get around this problem? Well, in small area estimation, it's all about saying, how can we borrow strength across the units? How can we steal information, if you like, from other areas, from other units in our sample to improve the efficiency of the estimator for the area that we're interested in, or the set of areas that we're interested in. So I can see the standard solutions, and those of you who work in this area, clearly you know these things probably better than I do. But basically what you want to do is you've got to collect some auxiliary information, some other information about the small areas, and you want to build a model that connects that auxiliary information to the outcome, the thing that you're trying to estimate. Now you can build that model, back in the late 70s, 1980s, really two approaches emerged, if you like, the unit level model, which came around in the 80s, and the area level model. And all that means is when it's at the unit level, you build a model at the individual units in your sample that connect the individual x's to the individual y's, and then you scale up using aggregates from the auxiliary data to produce your estimates at the end. Before that model came around, I guess that's like early 1980s was the first work there with Wayne Fuller and his colleagues. Before that, there was the unit area level approach, which, as the name suggests, you just build the model. You want to produce estimates for the areas. You produce a model that connects at the area level. Point being, it doesn't matter whether you go with this unit level model here or the area level model. At the end of the day, you're going to need these small area aggregates. You're going to need to know the totals of your auxiliary variables at the end of the day to be able to produce a set of estimates. So how does the classic Fay-Herriot model work? So this talk tonight is not about the mechanics of this so much, but just the basic idea here with the Fay-Herriot. You've got this set of small areas that you're interested in. Yi here, I'm saying that's the thing you want to estimate, that's the thing you want to observe. It's usually a mean or a total for the small area, perhaps can be a little bit more complicated than that, although the modelling assumptions probably don't work particularly well if it's anything too complicated. We've got our direct survey estimate that we've produced from our survey data, and then basically the idea is you say, well, that survey estimate should be an unbiased estimate, so it's really the true thing with some error term on it, and we make some assumptions about the behaviour of the errors, independence across the errors and so on. And crucially, we need to have an estimate of this sampling variance, this error variance for the relationship between this estimate and the true value of the thing that you want. And of course, that in itself is a big issue, in fact, when you really want to apply Fay-Herriot modelling in real life, because you might think, well, that's okay, I can just estimate this variance from the survey data, and in fact, that's what we do later on in the simulation. But you can understand, of course, there's a bit of a circularity here, because if my sample size isn't very big in my small area, then my ability to estimate the sample variance might also be somewhat damaged and difficult. And in fact, in reality, of course, when people do this, they end up fitting models on the variances and to smooth out what those sample variances look like. And then next to that, I assume that this true value y can be captured by some kind of linear function of this auxiliary vector x, this set of x's that I've collected, that I've put together, that I think should help explain the patterns that I see in the y's across the small areas. But of course, I know that those x's won't perfectly capture the y's, and so I allowed for the fact that there's this small area effect, this thing that might make one area a little bit higher than the model says and another area a little bit lower than the model says. And of course, the idea is that this E and this U, they should be independent of each other. Of course, if an area's true random effect is positive, its sample error could be positive or negative. There shouldn't be any relationship between the error that you see in the sample and whether that area happens to be high or low compared to the fixed part of the model, the bit that the structural parts of the model. So when you put the two things together, of course, you can estimate a model that says that the thing I observe, these direct estimates, should be this linear function of the x's here and the random effect u. So of course that's my true yi, and then plus the ei term on the end. So if I fit this model, and if you want to see how to fit these models, then so this is John Rao's latest edition of his small error summation book. So that's kind of got everything you need to know about how to estimate these models, and an awful lot more than I'm talking about tonight, of course. But the basic idea, the way I like to think about it, is that if you've fitted the model, this is the y here, the y hat, this is the thing you've seen. This is your fixed component, the x transpose beta, the beta hat's the estimated beta. So you've got this raw residual, this difference between what you saw from your survey and what the model says it thinks that area should be. And we know that raw residual, of course, if we go back to the previous slide, of course, that raw residual is kind of trying to get at the U and the E, because it's got those both parts in it. It's clearly helping us, hopefully, to understand about U, why this area might be high or low, but also it's bringing with it, of course, that sample error component as well, that extra noise. So what we do, of course, is we take that raw residual and then we shrink it using this factor that looks at that relationship between the variance that you are associating with U and the sample variance, the estimated sample error variance. And so if you look at that, then here when you rewrite it out, and this in blue, this is the way that most people write down the Fay-Herriot model. I just think it's nice to think about, what are you doing here? You're working out a raw residual, and then you're saying that raw residual has these two parts in it that shrink out the sample error part and leave what we think is reasonably the part to do with the actual small error. But the way that it's often written is the other way here, is to say, in fact, our Fay-Herriot estimate is just this weighted average of the two ideas. You can either have the direct estimate coming from the survey, or you can have this pure synthetic model estimate that's just the x beta component, and you're just shrinking, moving your weight between those two things. And if you look at this gamma here that we've got here, you can see that as the sample error decreases, so as you move into an area where the sample size is maybe bigger, and therefore you think you're going to have a more stable estimate from the survey there, you can see that gamma function there. As this thing decreases, the gamma goes towards 1, and so you are moving towards something that's very close to the direct estimate. It says that raw residual, most of it should be the random effect, and so you stick close to the survey estimate. But if you're in the other extreme, where you've got an area that's got very high sampling error, I'm not tonight talking about the other problem, which is when you have no sample at all in an area. That's another whole big issue as well. So I'm not talking about that issue tonight, but you can have areas where the sampling area is high. In that situation, you can see what happens is it shrinks it towards our synthetic estimate. I'm sorry here, I did some fiddling around. Don't fiddle around with your slides in the afternoon, obviously a bad thing. I decided that instead of, I had written this as, oh, it could just be some general function of x. I thought that sounds a bit silly. I just would write it in the normal x transpose beta form here, just a linear model. So here, basically, you're either shrinking, you're either moving towards staying close to the survey estimate, or you're shrinking towards that model-based synthetic estimator, because you're saying most of that residual I can see, I think that's the sampling noise, I think that's the noise in the estimate, so I don't want to include that in my small area estimate. In other words, what you're actually doing, because if you think about it certainly from under our repeated sampling framework, design-based, we would think this starting thing, this y hat, it might have a big sample error, but it should be basically unbiased for the thing that we want. And so what you do when you fiddle around with small area summation is you're kind of trading a little bit of bias against reduction of variance. You're saying, let's move to something that I think has a lot less variance, even if it might have a little bit of bias compared to the direct estimate. So to make this work, of course, and this is the point of the bit we're going to do in a second, to make this work, you need to have these x's. You need to have some auxiliary information, these aggregates that you think those auxiliary variables might reasonably be related to the y to help you build that model and get that variance reduction. And that, in a sense, can be quite often the limiting situation in real cases, particularly as you start to produce much more complex things for y. You know, maybe if you're measuring quite simple things in y, you might have some quite simple auxiliary data. But as you want to push that forward, then potentially the kind of scope of x's that you have available, starts to decline. And so that can, in a sense, be a limiting situation. So this is the idea. So this is back with Ybarra and Sharon Law back in 2008. They said, well, let's look at what we do. Can we open ourselves up to the possibility that instead of having these x's observed directly, that the x's themselves can have some measurement error in them, and how do we make that work? Can we make it work? And so the idea here is they're allowing you to bring in independent estimates of x's. So the x's mustn't be estimated in the same survey as the y, otherwise you're going to create correlations in errors, which are going to be naughty. So you want the measurement error to be independent of everything else that's going on. So you can bring in these independent measurement error auxiliary variables. And they were thinking about this in the context of the American Community Survey in the US. And of course, the American Community Survey came in the early 2000s and replaced the long form data in the census. So of course it meant that you're now getting quite regular updates of some of these measures coming from the American Community Survey, but they are very definitely coming from a survey. And although it's a large survey, and potentially when you combine across years, a very large survey, there's still going to be some errors. In our application, we're actually thinking about the census in Indonesia, but actually thinking about the 10% long form sample within the census. So again, it's very Indonesia's 10% sample census is big, very big, but still nonetheless, once you start breaking it down, you're going to bring some error with that. You're not observing those x's directly. And this is the structure here that we're looking at tonight. Different ways to do this, but we've got the idea again that the x that we're seeing, the thing that we're measuring, is the true thing, the thing we'd really want, plus some measurement error. And of course, this might be a whole set of these x's, and so you might have here actually a variance covariance matrix of the measurement errors. Some of those measurement errors in that C might be 0 because you may have some covariates that you observe perfectly and some covariates that you have a measurement error. And how does this work? So in the classic Fay-Harriott, you do the same thing. You end up with this weighted average between the direct estimator and your estimator from the model, the X transpose beta. But this shrinkage factor now gets changed because it has this additional component that comes into it, which is being driven by this measurement error component. And you can see that because that component is adding on the top and the bottom, it's essentially making the model variance bigger, which means that the model variance will become relatively more important compared to the sample variance, which means that for a given sample variance, you'll stay closer to the direct estimate. So it says because of the measurement error, we shouldn't rely so strongly on the results we're seeing for the model. So to have a look at this, if you have read Ybarra and Law's book paper, you'll see that they have a simulation study there. The results are quite difficult to actually pin down what the genuine effect was. They did a model-based simulation. They had a mixture of some areas with no measurement error, some areas with measurement error, and it was a little bit tricky to see, well, actually, what is the benefit? At the end, they demonstrated with the American Community Survey they could make the thing work, could get good results. But interestingly, what they didn't do in the paper was they didn't show you what would have happened if they just used the American Community Survey data and closed their eyes and not worried about the problem. So we were interested to see how this actually works. So ICA's been setting up this simulation study so she can use it for other tools as well. But the idea here is we've created a fixed finite population, a Y variable that we're interested in. We've got two X variables that we work with, that we generate X1 and X2, and we make it so X1 is relatively more important for predicting Y than X2, although they both they both contribute to predicting Y. We set the population up. We've got 100 sub-districts, 10 villages in each sub-district, 50 households in each village, and that creates a finite population that we can sample from. We then take samples, a stratified two-stage sample, to estimate the Y, to give us a direct estimate of the Y. And then we have different setups depending on what we're trying to look at. So one setup, we say, well, we know the true values for the X1 and the X2. We've got those available in administrative data. That's obviously the perfect situation, the one that you would like to be in. And we look at what happens there if we just use X1 on its own, just use X2 on its own, or what we really want, which is the true X1 and X2 together. Then to generate the measurement error, we take samples independently from the population to enable us to estimate X1 and X2 independently of the Y. And within this design, we actually have different sampling fractions for different areas in the different sub-districts, because if you have a common, very close common measurement error, they say it might have any impact. So you need to have some differences in the measurement error. That's why in the Ybarra and Law simulation, they actually made it very obvious. They had a whole bunch of areas with no measurement error and a bunch of areas with measurement error to maximize that. What we've done is try to think, well, you might have a sample design, it's got different sampling fractions, so it would potentially have different errors coming through then. And then what we do is we try out different scenarios, one where we say X1 is known properly, X2 is coming from the sample, the other way around, when X1 comes from the sample, X2 is known, and we don't bother to do any correction. We just treat them as if they're just normal covariates, shove them in, do Fay-Heriot, and see what pops out the other end. And then we compare that, of course, to actually saying, well, let's try and do this correction. And it's not obvious here, but we are two things. One, we do properly estimate. So if you go back here, of course, we said to make this work, you've got to estimate this thing. So this sample error variance in the Y sample. So we are estimating that in using a standard variance estimator within each iteration. So we do actually bring forward the fact that you might get some noise from your estimate of that. But in this work so far, for the measurement error side, we haven't tried to estimate the measurement error variances inside each iteration. So we've kind of assumed that God has very kindly told us what those measurement error variances are going to be. And obviously, you can see that's obviously going to just add another layer of complexity in a real application where you would have to bring forward estimating those things as well. Okay, so here's some results from the study that we've done. So here, this is just, I've got the variance results here because they're probably, I think, the most interesting. The one on the first one here is the variance. So this is just the empirical variance across the simulation. We've repeated the simulation 1,000 times, I think it is. And then you're just working out the empirical variance, plotting them out. So you can see most of the areas, the variance is not too bad, but we do have some areas where trying to estimate for them is really, they've got very high variances. So the first three then, next to that, are saying, well, what would happen then if you actually have proper X1 and X2 available? So the first one of those three is what happens if you use X1. You get the biggest gain there of the two on their own because X1 is the variable that has a stronger correlation with Y than X2. So when you put X1 in, you get some pretty decent gain. X2 doesn't do as well as X1 on its own. That's the second bar in that block. But again, because there is a correlation there, you get some good improvement. And then the third one is where you'd like to be, which is X1 and X2 both in the model, because, and in this case, of course, it's a simulation. There is a direct relationship between Y and X1 and X2 at the household level, so no surprise that when you look at that aggregate relationship, you get a really big efficiency gain there. In the next block here, this is saying, well, what happens if I do the same thing, but one of the covariates has measurement error in it? So in the first one of those two is X1 still being correct and X2 being added in, but with measurement error. And I think the nice thing about that, of course, is it shows this is the last one in the green is that perfect situation, X1 and X2. This one shows you that you can take X1 on its own, bring in the noisy X2, the measurement error X2, and you won't get quite as good as if X2 was the real X2, but you can do pretty well out of it. The other one shows that still it's worth it in a sense, but this is the other way around. X2 is the real, is the true one, X1 is the noisy one. But again here, because here you can see this is that middle bot there is X2 on its own, bringing in the noisy X1, of course, still improves situation for you, although you can see here there are some areas where it's not working quite so well. And then finally on the end, of course, it said, well, let's do the correction for measurement error. And I'll give you a few minutes to decide whether you think it's worth it or not. All you're seeing here, of course, is that because the measurement error says rely less on the model and rely more on the direct estimate, you don't get as much variance gain. So you don't improve you still improve the variance a lot, but you don't improve it quite as much as if you had not worried about the measurement error correction. What you do get is potentially a little bit of protection on bias because you do a little bit less shrinkage. But that's why you're paying the variance price, because you're not shrinking as much. That means you don't have as much bias, but you have more variance. Where we have tried to, we think we might find an effect is it does seem like, and I think this is something that we see in other situations in it, is that you can estimate the incorrect model, but what might go wrong for you is estimating the standard error and therefore the confidence interval. And what we think we're finding is a bit better confidence interval coverage when you make the measurement error correction. So if you like, when you don't allow for that extra uncertainty in the X, your model might think it's doing a bit better than it really is. And so when you construct the confidence intervals, you don't do quite as well as when you construct the confidence intervals using the correction. It's not a clear advantage. That's why I didn't put a nice slide up here to go, there we are. But that looks like a little bit what we might be getting. So from this first part, what's my take home? And I'm about halfway through, but Luca told me if I didn't want any questions, I should just talk for the whole time. Dangerous point. As Bernie pointed out, it's a dangerous thing to say to me. I think the main takeaway for us is that I think we can be a little bit more open about where we go and look for our covariates. and a richer source of covariates. And you can imagine in the Australian context, we do a lot of surveys which we might want to produce small area estimates for. We also produce a labour force survey, which is a much larger ongoing survey that might actually be able to provide us with some covariates that might actually be useful for small area estimation in other contexts. And in fact, in that situation, you have the opposite to what we had in our simulation, because we made the noise in X worse, if you like, than the noise in Y. We had smaller samples for X than we had for our Ys. But if you're doing it that way around, you're going to have a bigger sample for the X than you would for the Y. You do need to have those estimates of those error variances to make the adjustment work. In the end, I think we found that we're finding it hard to find, the impact of making these adjustments. Clearly, when you put measurement error variables in the model, you don't do as well as when they don't have measurement error. But the value of the adjustments is hard. Nico's now working on the unit level models as well, and it's hard to see the effects that you get from making the corrections. And I think in my head, it's like, well, classic measurement error is all about, I need to get this beta coefficient on this X variable because I'm interested in that relationship with Y. And therefore, when I have measurement error on X, I'm worried about that because it biases my beta coefficient and I'll make the wrong inference potentially about my beta. But in this small area model, I don't care, nobody even talks about the betas, right? Other than to say, oh, that one goes up and that one goes down and that's what policy people think should happen. It's there just, if there's a correlation, it's going to help you in your small area estimates, yeah? But say we do think we are getting something in terms of better standard errors and it does give you this biasing, but say the biasing is coming at the price of variance because you're just not going away from the direct estimate as far. Okay, second topic I want to talk about, this is one that I've worked on for a long time, but in various forms. So I want to talk about this idea of estimating a fixed population size. And in the context of official statistics, that's often we're trying to measure the census coverage. We've done the census, we know it didn't quite get the full population. We're trying to estimate what we think the full population would be. And these ideas often, they're basically, a lot of them around this idea of capture, recapture. I go into the population, I count it once, I go back again, I have another go at counting it. I hopefully can mark in wildlife populations, they typically do mark things in some way. With humans, I don't think Andrews would get permission to suggest that we stamped people in Australia when they filled in their census form, so that you make doing the post-enumeration survey a whole lot easier. They're also used in human populations for some of these hard to reach unusual populations, like measuring a population of drug users, for example, where you might have multiple clinics, so you see people in different clinics and then you try and link across. So in the census context, so the two things are typically what we've done the census. Shortly after we do a coverage or post-enumeration survey, we match between those two captures and we use that information to construct an estimate based on this dual system estimation idea. And dual system estimation, not new, it's been around for a long time. The idea is you've counted one list, so you know how many people are on list A. You then go and have another go and you count again on list B. And by linking those two things together, you can work out how many are on both, how many are on A only, how many are on B only. And in the way I've drawn it here, using that column there, I use the relationship in the column there to understand what I think the coverage is in list A and pop up an estimate of the total. That's classic dual system estimation. Implementing it's a little bit more complicated than that. I haven't talked about the fact that, of course, list B, when we do a coverage survey, isn't really a proper list. It's a survey, a whole bunch of other stuff, but that's the basic idea. Even in that basic form, of course, you're trying to magic a piece of information, which is this estimate of the total, no free lunch, got to have a closed population. Yeah, so there are good stories about wildlife populations where they've gone to lakes, caught some fish, marked them, come back a week later, tried to catch the fish, couldn't find any that they'd marked, had another go at marking them, come back, and then they worked out that by marking the fish, it just made it easy for the predators to eat them in the week in between. So the closed population assumption doesn't always, it's not so straightforward. And obviously in a human population, you know, we've got a sense of what we think the population is on census night, but of course the coverage survey doesn't take place at exactly the same time, so there are issues around that. Linkage between the captures, so in the census coverage survey thing, a whole lot of work done in ABS to be able to link those two data sets. You're not thinking about that problem tonight, assuming you can do that linkage. That's a non-trivial assumption, I understand. Independence between captures for an individual. So can't be any kind of structural relationship between how you respond in the census and how you respond in the coverage survey. And we spend a lot of time trying to make sure that we think that's right. There should be independence across individuals within a capture as well. You shouldn't have interrelationships in there. People tend to worry less about that assumption. And then this one about homogeneous capture probability for one of the captures. So within the structure that you do this table, you need that homogeneous probability assumption for one of them. Okay, that's boring. So that wouldn't have, Eman wouldn't have got much of a thesis out of that. So we tried to think about a little bit different way of thinking about things. And we fell on this idea, and it wasn't exactly how we started, but what a lot of countries are trying to do is think about a future that's post a traditional census. Now, some countries, like where Sweden, for example, where our esteemed chief methodologists come from, they've been doing this for ages, right? They've got all their lovely registers and it's all beautiful. I understand, obviously, in Australia, people still tell me about the Australia card fiasco, right? And so a population register is probably not appearing in Australia in any time soon. And Australia is not the only country in that situation. So what countries are doing is they're often bringing together their administrative sources and trying to create what they think might be a population spine for the country. And this is the basis of actually the PLIDA data set, the person level integrated data asset. That's much more than just the population spine, because it has a whole bunch of other data and variables in there. But at the heart of it, there's this initial list of individuals that we think these are the people who should be in Australia. How do you get on the spine? Well, you have to be in one of the input administrative data files. You might be in more than one of them, but you may come into the spine because you're only on one of those input data files. So you need to appear somewhere in the system. One of the problems, of course, with this, and I'm going to talk about this problem tonight, but again, it's another big issue, I understand, and that's the overcoverage problem when you start putting these things together, that people stay in data files when they probably don't belong in there anymore. So certainly when I came to Australia, when migrated here, I made sure the tax office knew the day I was leaving because they owed me some money. Yeah. But the NHS was still writing to us a year later saying, hey, you haven't come in for your vaccines recently. Would you like to come into Southampton for your vaccines? And it was like, no, not really, because we're now in Australia. So we know that there can be those. So what organisations are doing is they're typically bringing in rules. They use business rules to get rid of people who they think don't belong in the population. And if you like, one of the reasons around that is you end up probably saying, I need to get rid of the overcoverage. And as a result of that, I might actually even induce some undercoverage because I might end up getting rid of some people who really do belong, but my business rules don't support them being there. So if you have a spine like this, what might the setup look like? And this is where we started to think about it a bit differently, because people would often say, well, it's just going to look exactly like that, right? You're either on the spine or you're not, and you're either in this coverage survey that you might overlay or not. So we said, well, perhaps you can think about it a little bit different, because there are two ways you can be on the spine. You can be on the spine because you appear on many things, or you can be on the spine because you only appear on one of the input data files. And those people might not be the same. I mean, it seems quite reasonable to assume those people may not be the same. They may not behave quite the same in the population. And then, of course, you've still got some people that you might have missed. And so then when you want to do your estimation, you've got a couple of choices. You could say, well, I think the first row, people on multiple lists, that's what's going to tell me about the people who are missing. So I take that relationship to drive my estimate of the missing. It's like doing a dual system estimator with the first row and the third row. Well, I might think it's more like this row, right? Perhaps the people who are only on one list, they're more likely to be closer to the people who don't appear anywhere in the data. So I take that row. So it's like doing a dual system estimator with the second row and the third row. Now, of course, the point is I can't tell which one of those two I should do. And unless I'm incredibly lucky, those two approaches won't give me the same number in the corner. Now, I could also do that. That's the idea. Just combine the two rows together and use that in a dual system approach. At least with that one, I can check whether that makes sense, right? Because I can check, if I fit the log linear model, I can check whether in fact the first and second row have the same relationship or whether in fact they have statistically different relationships. So I can check if that one works. But these two are essentially saturated models. So I can't tell which one I might want to use. And they potentially, well, not potentially, they're likely to give you different estimates of the information that you're missing. So what we want to do is, well, how can we make some progress on this? And if you just take a single 3x2 table, it's pretty hard to do much. I've pretty much shown you what you could do in those slides there. But if you add a covariate in and embed a covariate, so you're basically splitting that table up into subtables based on a covariate, you can start to get some distance. And why would we do that? Well, in fact, because that assumption about homogeneity, often we need to break things up by covariates to actually make it more realistic that we'll have a homogeneous coverage assumption for one of the lists inside those subtables. So in fact, we do this, we go back to the US approaches in the 1990s, they talk about post-stratification where you split the population up into subtables. And Bernie worked on this in his thesis, and we won't talk about the distance between when we did the thesis work and we published the paper, Bernie, but there was a distance between those two events, but we did finally publish a paper. It took Peter Smith coming all the way from England to get it to happen, but we did manage it. So in Bernie, he had actually the setup from the Census Bureau were exploring, which was a 2x2x2 setup. So they were looking at the idea of having their traditional census, having their survey, and then also having their administrative source as well as a third source. So I had a 2x2x2 setup, and then we embedded a 4-category variable that was targeting this idea of homogeneity. So they created these classes within their data that they said these should, to do with renting and different backgrounds and so on. And what that showed us very clearly is that you can have much more flexible models for estimation in that situation, but this issue when you have more models, every time you try a different model with a different structure, you get a different estimate. Now, some of those models, it's easy to go, that model doesn't fit the data well, but as you get closer and closer to the saturated model that you can fit to the data, you get to a point where models that are very close to the saturated model are not statistically different from the saturated model, but they appear to give you quite different numbers for the cell that you're missing. Now, sometimes there are very wide confidence intervals on those estimates. You might go, well, in fact, maybe they're not really different from each other, but certainly they look very different, and you can't really pick between them because statistically, the different models all fit the data the same. So what Bernie did was he tried out, said, well, let's try, and at the time, it was a fashion for a while. Latent class models were going to solve everything for census coverage. Log linear models just bring a latent class. Lots of discussion then about what that latent class actually means. But I think for us, in the end, what we came out with, yes, we got a latent class structure out, but rather than think about that, it's more about potentially the latent class is just a different way of parameterizing the dependent structure in your data. So it's a different way of doing it that might capture that dependent structure a little bit differently. And that was the kernel of the idea that we had with Imam's thesis, that maybe what we could do is try a latent class model as a different way of capturing the structure that would lead us to an estimate. So you're going to do the log linear model setup for the 3x2x2. This is the idea. You've got our list, population spine. We've got the survey with its 2 categories. and then you've got some characteristic. We just got 2 categories. The idea for that, this is the minimum that will work for this setup. So I wanted to try in the smallest, like in the minimum situation. And if you fit the log linear model to the 10 observed cell counts, this is what it looks like. I've been very lazy here to write it out because, of course, here you don't get all of these for everyone, but if you're in 111, you just get the beta. If you're 211, then you get the beta 2 here and so on. So these are all the effects you get. So you've got the main effects for each of the the variables you observe, the list, the survey, and the characteristic. You get some 2-way interactions. And in the end, you end up here, we've got the 3-way interaction, which is just saying that for the second row in the table, which we do observe in both tables, we can have the interaction effect for the second row in the first table, and we can have a different interaction effect for the second row in the second table. But for the third row, we can't see the interaction effects because we don't see the second cell in that row, in that third row for each of the tables. So those are the 2 effects that are missing here from the full 12, in that last row, the interaction effect on the first table and the adjustment to the interaction effect on the second table. So we set this up, we use the EM algorithm to fit the models, you estimate the models, update the data, estimate the models. The issue is, how do you estimate the missing cells, those 2 missing cells when you're doing this? So option 1 is you treat the third row effects like the first row. So you just go, well, there's no interaction effect operating in the third row. So you just predict what you think those third row cells are using a model that doesn't have any interaction effects. Alternatively, you think, well, maybe the second row might be closer to the third row. So you say, okay, what I'm going to do is I'm going to do estimates of the missing cells, and I'm just going to plug in the second row interaction effects as a replacement for the third row. So here, I really would like this to be 3-2, but I can't estimate 3-2, so I plug in 2-2, and here I'd like this to be 3-2-2. Again, I can't see 3-2-2, so I just replace it with 2-2-2. And again, the choice here is obviously not statistical, because in both cases, I'm just saturating the log linear model. It's just how I'm choosing to fill in those 2 missing cells. But the saturated model will fit the data exactly the same. So the alternative, we said, well, let's try this from a latent class perspective. So we bring in the idea that we could have a latent class structure, 2 categories to latent class. And this is the simplest latent class model, of course. It says, given the latent class, there's no relationship between the 3 manifest variables over in the corner there. In Bernie's work, because we had more degrees of freedom, we actually fitted latent class models that did allow for some interaction effects still to be maintained after the latent class. So that's what the latent class model looks like. You write it out, you get all the main effects for everything, and then you get the interaction effects between the class variable and all the manifest variables, so that it allows you to have different relationships between the class, different effects for each of the manifest variables in the 2 classes in the model. Now, how did we fit this? Well, we didn't make up how to do it. There's a package called Polcar in R, which has been around for a while. It actually works on unit level data. We had to make it work for our aggregate data situation. Also, it doesn't do the updating for this missing cell like we needed to do. So we basically have a very nice paper that lays out very clearly what the algorithm is. So we could take the paper, we could take their algorithm and just apply it to our situation with our aggregate data. And the trick is that when you're iterating around, you need to update. You mustn't let the algorithm just run on the observed data. You need to keep updating the missing cell in the corner as well, so that you only do 1 iteration of the fit of the latent class model before you say, I've changed the model parameters in the latent class model, therefore I need to change my estimates in the corner cells. And you keep going around and you keep iterating. It takes a long time. When we first ran it, we thought initially it wasn't working, and then we realized simply because we weren't running it for anywhere near long enough to get it to converge. It converges quite slowly. So we've done a simulation. This is the data we've simulated from. So we've created this. I won't tell you where that comes from. It's a secret. I'll tell you at the end. But we simulated from those 12 cells just a multinomial draw from a multinomial model with that underlying structure. Of course, then you throw away the two cells in the corner, and that gives you the data. So here are some results from just a little bit of the results. So 12,177, that's the number, the overall total. So could show you breakdowns for estimated individual cells, but just for time tonight, just sort of show you the sort of high level picture, which is how well do you do at getting the overall total of 12,177. So if you just take the 10 observed cells, you say, well, that's what I know. Of course, you end up with not very much variation. It's a multinomial draw with a large sample that doesn't vary very much, but obviously it's not in the right place. If you, in this case, here we're using the first row interaction model. So when we use the first row of the model to fill in the third row, then things improve. Of course, if we put something into those corner cells, we get a little bit of increase in variation, of course, because we're estimating this thing, but we still are not in the right place. But if we take those values that we estimate from that model and say, well, we use those as the starting values in the corner for the latent class model. We did try starting at 0. It will get there if you start from 0, but it's very, very slow and it doesn't get there very well. So we thought if you start somewhere that's not completely miles away, these should be reasonably close. So we start with those. And if you start with those, boom, we end up with something now that's in the right place, but you're paying a massive price in terms of variance. That's the first row interaction. Now, you wouldn't know in real life whether that was particularly close or not, but it turns out that in our data set, if you start with the second row interaction, you're very close because, in fact, the second row interaction is quite similar in our data to the third row interaction. So if you start with the second row interaction, so you can see there, of course, if you don't do anything, you're miles away. Use the second row, you get a big improvement, move up to where you should be. Taking those as starting values, so you're not quite unbiased. You can see if you move then to the latent class fitch, it becomes again unbiased. But interestingly, you're paying the same big price in variance, even though you were already nearly close to where you wanted to be. So the variance still, even though you started much closer to where you wanted to be, you in fact still get this big variance price. The three, the blue, the red, and the green, they're just different initializations. So we did different random starts because with this algorithm, if you want, we haven't really nailed down how you're going to decide which would be your final estimate. But when you run Polcar on a standard data set, they recommend you should run it several times to get it to do different random starts and basically check that you end up in the same place so that you're actually converging to what might be the maximum likelihood estimates. This was a different way of doing this, is just using that simple model that doesn't have any interaction structure in it to give our starting values. But again, you can see same message. Yes, we start off relatively close to where we wanted to be with this main effects model, but we still get this big variance price that you pay at the end. So to finish, so what's the take-home message here? I think what we've been exploring here is again recognizing that population spine structure. So thinking maybe potentially about that as 3 by 2 instead of 2 by 2, and then bringing in those covariates. It gives you something that potentially is a little bit more flexible in terms of the models that you can fit for those missing cells, and gives you a bit more flexibility to play around with that dependency structure. Does seem like that latent class modelling is an alternative way to capture the dependency. Of course, the advantage here is the idea, of course, is that if you start off, didn't show you here, but if you start off in 3 different places, primarily the latent class model, you end up in the same answer. It doesn't matter which one you start with. Even if you start with 0, you typically end up more or less at the same point. Take a lot longer to get there, but it will get there. So you have a unique answer, if you like. It's a saturated model that gives you a unique answer, but you're paying a big price in terms of variance. One question to think about, I think, for us going forward is, one of the things we had with Bernie's work was we had, in the end, a lot more degrees of freedom than we needed for the model. And so 2 more degrees of freedom if we had more categories in the covariate, we'd start to become more flexible. We wouldn't be saturating the latent class model, might make things more stable. And of course, the real secret is that 12 cells there, we created them from a latent class model in the background. So although we don't generate from the latent class model, we know that in principle you should be able to split those cells to, that's why you get unbiased results. And of course, what would be interesting would be to start trying this in situations where you don't know that their latent class model will actually fit to the data, and then do you just get it blowing up and get no variant, no bias improvement, for example. Just a few references, the key ones there. And thank you very much for listening, and happy to answer questions unless you're all desperate to get to the Indian restaurant.
Any questions here from the audience? Yes.
Hello, thanks for your talk. So my question is along the lines of, if I were to approach this problem as a Bayesian, I'll just talk about your first problem because that's sort of easy to think about. So you've basically done quite a lengthy analysis involving the residual resistance, likelihood function, but I'm not seeing the prior. And so how would you go about doing things from a different point of view and doing a Bayesian?
Well, I'm not a Bayesian, so I probably wouldn't. But a Bayesian approach is very common in small error estimation. So because the hierarchical linear model structure is ideal for small error estimation, and so typically people would approach this setting up as a hierarchical linear model. How you would integrate the measurement error, I'm guessing that should be fairly straightforward in a Bayesian framework to bring in your understanding what you think the measurement error would be and estimate.
I mean, in a way, you're bringing prior information with that X, bringing some, by establishing that correlation, that's a way of trying to that place should have certain estimates. So in a way, you're approaching that. It's just interested to see.
Yeah, say I'm not, but certainly in the literature, and certainly I know, for example, in New Zealand, when they do their small error estimation for census coverage there in large scale, they do that in a hierarchical linear, Bayesian hierarchical linear model. So, and that's estimating actually a logistic small area model, and they use that.
Thanks.
Yes.
Thanks for nice talk, James. Two questions. You mentioned New Zealand, so my second question has actually to do, but the first one you probably can answer quickly, and that's when you looked at the measurement errors, how did you see any difference or any patterns depending on how big they were and so on in those studies that you did in the first one?
Well, yeah, what we found was that early on, when we had bigger sample size, we couldn't see any effects at all, right? I mean, we had to try and make the measurement error go big to start seeing any kind of effect at all, which is partly why we then cheated and said, look, we're not going to try and estimate the measurement error variance from the data because we're making the sample sizes so small to try and make the measurement errors big in the simulation, which means that it would have been very difficult to then try and estimate those variances directly. So the answer is, yeah, my feeling from what we've seen in our simulation, and it's just one study, I understand that, is that as soon as you get any kind of real signal between the X and the Y, in other words, there's enough correlation there for you to get a benefit, it's not going to make much difference.
Yeah, exactly, and that's when they're that big, you probably wouldn't consider them in the first place.
Yeah.
My second question was about, I mean, I know that you are informed of what they're trying to do in New Zealand the next time they do a census, which could be some sort of hybrid or at least a departure from the traditional census, and there's a history behind that and so on. But part of that is also using survey information a bit like the American Community Survey, where they collect Ys through surveys and so on. What you just talked about today, especially the second example, would you think that there are takeaways from this in their applications as well?
I think, well, the second example, I guess, is about whether you can leverage off the way you construct that first list. So instead of just saying, here's a list, and then I overlay a survey, if I know that list itself, people come into that list in different ways, potentially there may be some benefit to recognise that instead of just collapsing everybody together and saying, that's how many people I saw. So I think that would be potentially where it's worth thinking about how do people get into that list.
And I have a third one as well. Obviously, the census, you look at the difference or the change since the last one. I mean, that's the classic way of looking at official statistics. If it varies a lot from the last one, you start to doubt what you just captured, right? Would you think that previous census estimates could play a role in these parts as well, or if you want to kind of estimate a change measure instead of levels? Have you looked at that, or have you seen any of that?
I haven't thought about that at all, but I guess you could. I mean, obviously,
they're correlated, obviously.
The traditional approach in Canada was what they called the reverse record check, where they kind of did that. They took a sample, chased it up from the previous census to understand what they thought the coverage was in the current census. Certainly, I think in a small area.
I mean, that's what you do when you have a register base, right?
Yeah.
Because you have a person who lived 5 years ago and they're registered still, and so on. So you kind of use that.
Well, no, and I guess that's also what you're using when you construct the spine, in the sense that you're using the history of someone being there and their interactions to justify them being there.
Just one last question, maybe online. So this is from Tammy. You indicated this approach was very time consuming. What are your thoughts on scalability, suitability for the National Statistical Office?
Oh, sorry. The Lane class model. When I say it takes a long time, I mean like on the laptop, to do one iteration. I mean, we're doing thousands of iterations in the simulation. Do one iteration, you go and make a cup of tea in the scale of the problem that we're working in. I just mean that we naively thought the EM algorithm, the standard EM algorithm for a log linear model typically converges in 15, 20 iterations, let's say. This thing might take 1,000 iterations to get close to where you need it to be. It doesn't take a long time, though. Sorry, we're not talking days here. We're just simply talking that it's make a cup of tea time while it fits. But that's a lot of cup of teas when you're running a simulation.
Thank you.